but now we can also do time shifting and scaling together, right? So it is possible that you can shift the origin and then scale the signal about the origin. Okay, both are possible. Now, what should be the order in which we should do this? Should we first do the shifting or should we first do the scaling? So if somebody gives you some signal x of t and then says that, okay, now I want this signal to be shifted by b times and then scaled by a times, what would you do? So all this operation is doing is moving the origin, and about the origin you are going to either expand or compress. Okay, so the easiest thing to do, or my recommendation, would be to first shift, like I said, because this is representing only shift of origin and then expanding out about the origin. First operation would be to shift the signal. So if you have a signal, let's say, that looks like this, what do? You first shift it. First operation would be to just change the origin. Once you change the origin, now about this changed origin point, you either expand it or compress it depending upon what is the value of A is. Okay, so this is easier. So what you can do is you can first shift. The first operation would be to compute this. Okay, and then the second operation would be to just scale the time factor. Or if you want to do the other way around, that is still okay. Nothing wrong in that. But there is something that we have to keep in mind. Let's see what is that you have to keep in mind. Let's say you are first going to scale. So which means you are retaining the origin to be at 0, and then you are going to do the scaling operation. Either you are going to expand it or you are going to shift it. And then, so either you are going to expand it or compress it, and then you are going to shift it. Now, if you are going to shift after expansion, let's say, then remember, because the signal is already expanded, the amount by which that you have to shift also needs to expand. If the signal is already compressed, then the amount by which you are going to shift should also compress. So in order to ensure that this shifting and shifting operation incorporates compression or expansion, you need to scale the amount by which you are going to shift. So if you do the scaling first, then you have to change the shifting amount by the scaling factor as well. So that is one thing that you have to keep in mind. In other words, the first operation that you're going to do is compress the signal. If the signal is compressed, remember, you're multiplying already the time factor, the time variable, with A. So the shifting should also be done in the scaled variable. So because of this reason, to incorporate the compression or expansion in the scaled axis, we have to change this shifting factor as well. So if you scale first, then you have to shift by a different amount. But if you shift first, then there is no change of variables or no change of constants that is required. So it's easier to do the change of origin first and then the expansion or compression operation. So why is this required? So if you see what is going on, essentially you're performing two operations, either function 1 or function 2. So the function 1 can be shifting. So there is this t, and this t gets modified by this f2 of t, and then it gets modified as f1 of f2 of t. Okay, and then when you plot, what do you first plot? So you plot x of f1 of some variable v, and then how is this variable v obtained? You obtain it as some f1 of f2 of the time. And what is this f1 and f2? So f1 could be as simple as, let's consider this case where you shift first. Okay, if you shift first, then f1 is simply f1 of v is simply v plus v. Okay, and then this is, in this case, there is this v is a function of time. So v here is f2 of t, where what you are doing is scaling. In other words, v is equal to a times t. So you substitute this back here, then you get this to be equal to at plus b. Okay, so given a signal and then you are asked to shift and scale by some amount, essentially what you're doing is you're applying two operations to the time axis, and those operations are either shift or scale. And if you are supposed to reverse it, let's say now I give you a signal x of at plus b, and then ask for what is x of t that gave this x of at plus b, then you need to reverse this shifting and scaling operation. So how are we going to shift and scale it to get back the actual signal? So you have to take the inverses. And how do you take the inverse? So in order to take the inverse, you have to do this operation in the reverse order. So if I first shift the origin and then compress and scale it, then remember, when I have to do the inverse of it, I have to first do the compression or expansion and then shift the origin. So let's, for example, take this case where we obtained x of at plus b from x of t by doing the shifting operation first and then scaling operation next. In other words, f1 was shifting and f2 was scaling. So I want to now reverse this so that from x of at plus b, I'll get x of t. So how to do this? Because the scaling operation was the one that was done last, we have to do that now first to undo this entire thing. So how do you undo the scaling operation? The scaling operation should be done by multiplying with 1 by a. Okay. Scale, you multiply with 1 by a, which means if the signal was initially compressed, now you expand it. If the signal was initially expanded, now you compress it. Okay. And then you shift it by whatever was the amount that was required, which is minus b. Okay. So this is the reverse operation. So this first shift and then scale could be reversed by first scale and then shift. Now if you had initially scaled it first and then shifted, then that could be reversed by shifting first and then scaling next. And by what amount you should shift, because you shifted here by b by a, remember that is the operation first you are going to reverse. So you have to reverse it by the same amount. You're going to shift it by minus b by a. So if you have shifted it to the right, you will shift it back to the left to reverse it, and the other way around. Now you shift it and then scale it by the amount that was originally scaled. So this is the reversing operation. So this way we now know how to time shift and scale and also get the original signal back if the shifted and scaled version is given. Now let's see some examples so that we'll be a little more clear. So let's say we have u of t and then we want to compute u of 2t plus 1. Okay. How does this look like? Now let's do the shifting operation first. Okay. So we did the shifting operation first. So this has, okay, I'll make this minus 1. Okay. So minus 1 means it moves to the right. So this is u of t minus 1. Okay. And then now let's do the scaling operation. So if we do the scaling operation now on this signal, what do? So we keep the origin fixed as such and then we scale about the origin. In other words, when t is, so the origin here is 0 and this origin here is 0. Now because the constant a here is positive, there is no time reversal and it is greater than 1. Because it is greater than 1, it is going to get compressed. So the entire signal that is present here, you just compress it. So if you compress it, what do you get? Everything gets squished towards 0. So compression, remember, it's compression towards 0. So just squish the entire signal from either sides. So whatever was 1 gets moved to half. So at t is equal to half, essentially what you have, u of 2 times 1 by t minus 1, which is equal to u of 0. So the point at u of 0 moves to half here, and the rest of the signal comes as such. Okay. So this is how you do shift first and then scale next. Now let's do the other way around and let's see what happens. Now let's plot u of 2t first. So if you plot u of 2t first, the same thing. Remember, this is what we saw earlier. So because u of t extends from 0 to infinity as such, just by scaling in time, nothing changes. It's the same signal. Now, because we did the scaling operation first, the shifting operation should change accordingly, which means now we need to shift by b by a. In this case, b is 1 and a is 2. So now we are going to shift by half. So if we shift this to the right by half, there is a negative sign for b here. So if we are going to shift this by minus half, which means the signal is going to move to the right, what we get? We get this signal. Okay. So by the same techniques that we saw earlier, either shift or scale or shift, by both the operations we got the same signal. That's what we discussed, right? Either you can do one of the shift or scale first and the other one second, but you have to keep in mind what should be the right scaling amount and shifting amount by which you have to move the signal or expand the signal when different operations are performed in different orders. So my recommendation is always do the shifting first and then just squish or expand the signal about the origin. So it's easier. Okay. Now, what have we done in all these operations? If you just think about it, there is a map which is given to you. That is, if I say my signal x of t is something, what is that? It is basically nothing but for each value of t, I'm saying that t is equal to some a, then or maybe I'll use the value t naught. For t is equal to t naught, I'm saying that x of t takes this value, and then for t is equal to t1, I'll say that x of t takes some value. In other words, what is this entire thing? It is almost like a table, right? So you just draw a table and then say that t is this and x of t is this, right? So 0, you have x of 0, and then some minus 1, 1. Similarly, you have x of 1, something, x of minus 1 and x of 1. In other words, given a signal is nothing but a map. This is what we saw initially, right? It's a map. So given some value of t, a signal says, okay, it's a function. So I pass this value of t to this function and I get the corresponding number. I can plot this graphically as a graph as some t versus x of t. So when we are doing the scaling and shifting, what exactly are we trying to do? We are actually trying to come up with a different signal, x dash of t. Okay, and how are we obtaining this? We are obtaining this as some x of at plus b. So the time axis does not change. So that's the key thing to remember. So when you have t and then have x of t, and you get a different signal x dash of t, which is basically the time scaled and shifted version. The time axis in both these cases is the same. Okay, what changes is only this function. So essentially you are constructing a new signal altogether by doing this manipulation of time scaling or time shifting. So if you shift the time, it is almost as good as constructing a new signal. If you are scaling the time, it is almost constructing a new signal. So the signal is different, the time remains the same. So the x-axis in all these cases, it is invariant, it does not change, it is remaining as such. The only thing that keeps changing is for the value of time, what value x of t takes. That is the one that keeps changing. So when you try to compute x of at plus b, essentially what are you doing? You're generating a totally different signal. Okay, and that signal, let's call that signal x dash of t. It is related to x of t. And how is it related? It is related in this fashion, that when you have t to be, let's say, 0, you compute some other variable b, which is equal to at plus b, and then you say that at t is equal to 0, b is equal to b, and then let's say at t is minus 1, b is equal to minus a plus b, right? And then at t is equal to 1, this is equal to a plus b, and then you compute your x of at plus b. So how do you compute this x of at plus b? In other words, you are computing x of b. So the value here is x of b. So you search for x of b here. If b is minus 1, then this value appears here, okay? And then this is x of a plus b, and this is x of minus a plus b. So now what would be x dash of t? So this is x dash of t. Now x dash of t is essentially this value that we have here. This is x dash of t. So you can completely forget this column in between and then simply call this as a new signal where the map is given by this, where when t is 0 you have x of b, and when t is minus 1 you have x of a minus a plus b, x of 1 this is x of a plus b, and so on. So this is a total new signal, and that signal is your time shifted and scaled version. So as you can see here, this diagram, this Venn diagram sort of a thing explains this entire operation. So you just map the values of t here to x of t. That's your original signal. Now what you have to do, you have to come up with a totally new signal. In other words, you have to create this map which is between t to x dash of t. Okay, but remember, this t, this domain remains the same as such. Only thing that changes is at t is equal to 0 or t is equal to 1 or t is equal to 2, the value that is taken by the signal, that keeps changing. So this domain, the domain to which it gets mapped, the image, that is one keeps changing. Okay, so this keeps changing. And how does it change? This is how it changes. Okay, so you transform it by changing the value of the original signal itself. So in other words, whenever you want to scale or shift, what do? You take these, let's say for example this signal here, you take these important points where the function changes direction or changes the slope or changes the shape. So this is one point, this is another point, this is another point, right? So these are the points. Let's say at t is equal to minus 2, t is equal to minus 1, t is equal to 0, and t is equal to 3. Now if you want to shift or scale this signal, what you have to do is see what happens to these points. Where do they get shifted? In other words, t is equal to minus 2 gets moved to a times minus 2 plus b, and t is equal to minus 1 moves to minus a plus b, and 0 moves to just b, and 3 moves to 3a plus b. Now you can compute the new signal just by drawing the time axis. Okay, so at t is equal to minus 2a plus b, you can draw this line. Okay, now let us say a is equal to half and b is plus 1. Okay, if a is half and b is plus 1, just substitute those numbers here. So what do you get here? If A is half, you get -1 plus B, which is 0. So which means this line, this entire line that was here, comes here as such. Okay. Now let's see what happens to -1. When it is -1, then we get, oh, sorry. The point -1 now moves to -half plus 1, which is plus half. Okay, this is 0, this is plus half. Now the 0 point moves to plus 1. So this is 1. And the 3 point time t equal to 3, that moves to 3 by 2 plus 1, which is 2.5. This is 2.5. Okay. So as you can see here, if you just keep this table of operations in mind, this entire thing, how to map one signal to another signal, just by looking at these points, you can just take these points, time t is equal to, so the what are called as critical points, basically the points at which the signal changes shape. Okay, just take those points and then see the time values there. Okay, and then see how those time values are changed, and then just put in the corresponding time values in the new signal, and then you can compute your time scaled and shifted signal accordingly. Okay. Let's see more examples now. Now I want to compute what happens to this ramp function. This is a regular ramp function, right? This is r of t. 0, one of the points is 1. Okay. Now let us see what happens when A is -1 and B is, let's say, 2. Okay. Now when A is, so for t is equal to 0, we know that any point here now gets mapped to AT plus B, right? So for t is equal to 0, AT plus B is equal to just 2. And when t is equal to 1, AT plus B is equal to -1 plus 2, which is 1. And what happens when t is equal to, let's say, -1? Then we have AT plus B to be equal to 1 plus 2, which is 3. So if you plot this, what do you get? At t is equal to 0, we have 2. At t is equal to -1, we have 3. At t is equal to 1, we have 1. What about t is equal to 2? At t is equal to 2, we have AT plus B equals 0, which is R of 0, that is this point. So now the entire signal looks like this. Okay. So now we have done this operation in a different fashion. Remember, we did not do this shift and scale. So we said we can shift first, scale second, or scale first and shift second. That is one way of doing this entire operation. The other way is just looking at the critical points and then see what happens to this values of the functions at those critical points, and then directly plot through this. So we got the signal. Let's do the same thing now with the shift and scale. So let's first shift. So if we shift first, let's see what we get. So I'm going to shift the ramp by 2 r of t plus 2. So this b is positive, which means that it will get shifted to the left. Okay, at t minus 2, 0. All right. So now this is the shifted version first. After this, you have to scale. Now the magnitude of A is 1, which means there is neither expansion nor compression, but the sign of A is negative, which means there is time reversal. And how are we going to reverse? The reversal is about the origin, about the y-axis. So it's like just taking the mirror image of whatever was existing, just flip it about the y-axis. So whatever is on the left side comes to the right, whatever is on the right comes to the left. So the entire thing just moves like this. Okay. So whatever is minus 2 comes to 2, and whatever is at, let's say, 1 comes to minus 1. Now we get back the same signal here. Okay. Let's do the other way around. Let's first scale it. So let's scale by minus 1. So once again, magnitude is 1, so there is no compression or there is no expansion, just reversal. The entire thing just gets reversed nicely as such. Okay. So whatever remains as such. So this point will be 2. This point will still be 2. Now let's do the shifting operation. Now remember, because we scaled by minus 1, now the shifting should be done such that the shifting constant is also scaled accordingly. This shifting constant was 2 and the scaling is minus 1. So this is 2 divided by minus 1, so minus 2. So if you are shifting by minus 2, what happens then? Remember, a negative shift means you have to move to the right. So you move this to the right. You move this to the right by 2 time steps. That's it. So you get the same signal once again. Once again, this is the same thing as this. Okay. So we have seen here 3 different ways of doing this time manipulation or this independent variable manipulation. The first way is to shift and then scale, or scale and then shift, or just note down the important critical time points, transform them, and then plot what happens to those points in the graph. So there are 3 different ways of computing this new signal. So remember, this is a new signal altogether, and this new signal can be obtained in 3 different ways, and this is what we have seen now. So in similar fashion, you can compute what happens to this rectangular function and this cosine function. Okay. So in the next lecture, we'll see some more examples of what happens to different signals when we scale and then when we shift.